Why do some reactions occur in a flash, like a sprinter racing to the finish line, while others plod along, seeming to take forever to finish? Imagine an obstacle course. One step always slows everyone down. Maybe it's a towering wall or a tricky rope climb. In chemistry, that obstacle is called the rate-limiting step, and it controls how fast a reaction can go. Let's break it down and find out more. This is Real Chem. In chemistry, we measure how fast reactions happen by timing how quickly products form. It's just like watching people cross the finish line in an obstacle course. But here's the twist. If the course has a tough section, like a giant rope wall, that single step sets the pace. Chemists call this the rate-limiting step. Understanding this concept lets us predict how reactions unfold, even the complex ones. Let's dive in and see it in action. In a single-step reaction, the rate depends only on the rate of that single step. One example of a step in a chemical reaction is when two molecules collide to form a new species. Another is a molecule breaking apart. Think of it as an obstacle course with only one obstacle, like a rope wall. The rate is whatever it takes to make it over this wall. But what happens in multi-step reactions? Let's add a small hurdle after the rope wall. The rope wall will still set the pace because once the racer conquers the rope wall, they quickly jump over the hurdle to make it to the finish line. The rope wall is the rate-limiting obstacle. Similar situations often arise in multi-step chemical reactions where there is one step that is much slower than the others. This slowest step in a reaction sets the pace. It's called the rate-limiting step. Once someone conquers the rope wall, they usually finish the course quickly, just like fast reaction steps after the slowest one. Let's look at an example. Two nitrogen dioxide molecules react with one molecule of fluorine. Once the reaction is done, we find that it produces two nitrile fluoride molecules. Let's say that the reaction occurred in one step. The reaction rate would then depend on the frequency of collisions between two nitrogen dioxide molecules and one molecule of fluorine. This would give a rate equation with this dependence on the concentration of the reactants. The concentration of nitrogen dioxide is squared because the collision involves two of these molecules. The concentration of the fluorine molecule is raised to the first power because the collision involves one fluorine molecule. But it's more likely this reaction actually happens in two steps. In the first step, a molecule of nitrogen dioxide reacts with a molecule of fluorine. This reaction produces a molecule of nitrile fluoride and a fluorine atom. This step happens slowly. The rate of this step is shown here. When we say this step is slow, we mean that the rate constant for this step, K1, is small. In the second step, the fluorine atom formed in the first step reacts with another nitrogen dioxide molecule to form a molecule of nitrile fluoride. This step happens quickly, that is, K2 is big. The sum of these two steps gives the overall reaction. Because the first step is the slow step, equivalent to our rope wall, it determines the overall speed of the reaction. This is a clear example of how the slowest step, the rate-determining step, controls the reaction rate. Therefore, our rate of reaction will be represented as follows. As you can see, we don't include the fast step in our reaction rate equation. Think of it this way. If you're designing an obstacle course, knowing which step slows people down the most helps you predict overall times. Similarly, chemists identify rate-limiting steps to understand reaction rates. To sum it up, in both obstacle courses and chemical reactions, the slowest step sets the pace. So the next time you study a chemical reaction, look for the bottleneck. Which step is the rope wall? Answering these questions gives you the power to understand and speed up chemical processes.